Okay, I'm going to go back. We're about to enter number 4, but I just thought I'd finish off 3, even though I botched one section quite badly. I would like you to always do the review at the end. That's your best way of doing well on a test, is doing problems. Don't waste all your time memorizing formulas without practicing with the problems, because memorizing the formulas, the ingredients, practicing problems is baking the cake, and during the test you realize that baking cakes is what it's all about. But I want to go back to this one question here, which I know the techniques I was showing on these last questions were right. I was just botching the numbers, and that's fatigue. I'm going to go back to this one, which is actually quite interesting and well worth doing. There's something coming up. And that looks at this one. So think of this weird shape. They're making a gutter out of it, and they're taking a flat piece of metal, and they tell you right away, you know, this metal is 5 long. That's that part there. And they tell you this length here, total, is 60. And as you can see from this diagram, they bend it here and here. And if you look at this, this is a constant. It's 5. It's not changing. They're telling us we're stuck with this 5. So to maximize the area, it's going to be this shape times that 5. Since that 5 is consistent, to maximize area, we really just have to maximize this shape here. And that's a trapezoid. It's a trapezoid. And we don't have much information about this trapezoid. The only information we have is that this red length plus this red length plus this red length is the same as this total length over here. Okay? So we know that total is 60. All the way around, 60. And we also know this is 180 degrees, and this is 180 degrees, 120, and 120. And we don't know this, except we know it's going to be parallel to that, because that's what we're building. So when this is parallel to that, it automatically tells me that these sides here are going to be the same length. They have to be. There's no way they could join this parallel object up above if they weren't the same length. If this one was longer, it would be slightly inclined. It also tells me that if this is 120 and this is 120 for 240, we have a total of 120 left in these angles, which means this one corner is 60 and this one corner is 60. Now this is important, because normally to calculate a trapezoid, you're averaging this length and this length, so A plus B divided by 2, and you're multiplying by the height, which is that. Well, we don't have that information, and we don't have the length up here, which means we need another system for measuring those. Well, we have quite a bit of information. Since this length here is the same as this length, we can call those x. We're going to call this y, this length here. And we know that x plus x, which is 2x, plus y, is equal to 60. So we have a formula right off the bat. Now looking at the shape here, I'm going to focus on drawing a line here. And I'm going to focus on that one triangle. And there's 2 identical ones on either end, okay? But I'm going to focus on this one area of this triangle. If I look at that in a bigger picture, like that, and it started off like that, I know that this thing is 120. And I know that this angle up here is 60. Okay? If I draw a line straight up, which is what I have to do to determine a height at 90 degrees, I now know that this tiny angle here is 30, so we can get rid of that. So let's just concern ourselves with this triangle now. And we would like to have a measurement for that. And we'd like to have a measurement for that. Okay? And you might say, well, why do I need a measurement for this? Because that's going to be the formula for the area of this triangle is half times the base of height. That's going to be the base, and that's going to be the height, and that will give me the area of this triangle. And the only information we have is x and these angles. Well, thanks to SOHCAHTOA, we know that the sine of 60 is going to be equal to the opposite, which is this side, over the hypotenuse, which is x. Rearranging it, we now know that the opposite length is the same as x times sine of 60. Fantastic. We now have a measurement for this length here. And we also know down here for sine 30, it's going to be equal to the opposite, its opposite, over the hypotenuse, which is x. Rearranging that, we realize that the opposite length is the same as x times sine 30. Great. Now we have a length. Using this formula now, I can say that half times this length times this length is going to be the area of that triangle. And don't forget, there's another one on the other side that's identical. So we're going to multiply by 2. The nice thing about that is these cancel out. And x times x here is x squared. And since sine 30 is just a number between 0 and 1, and is sine 60, we're just going to put them and leave them there like that. This is now a formula for the area of the two triangles. Now I just need to figure out this. Well, I know that's y times the height, and I just figured out before that the height is sine 60 times x. So that is the area of the middle. So if I add these two together, that's the total area that I have to maximize. Well, my only problem is I still have a y in there. Unfortunately, that's where this comes in. If I rearrange this, I get that y is equal to minus 2x, which means I can replace y with that in brackets. And that's where everything gets confusing. Okay? So that's a 60, not a sine 60. Just keep that in mind. So if I were to expand this, I'm going to get 60 times sine 60x minus 2 times sine 60 x squared. Okay? That's the expansion of that. And then I'm going to add it, right, to, did I have more than that? Yeah, I'm going to add it to sine 60 times sine 30 x squared, which I believe makes sense. Just be aware that sine 60 and 60 are two different numbers, and then essentially these are just numbers in front of our x squared. We can't add these even though there's like terms. However, we can see that there's a sine 60 in each of them. So we need to take the derivative of this. And you might say, well, I haven't gotten derivatives of sine 60 yet, or sine yet. Well, you don't need the derivative of sine yet because that's a number. So that's just going to be a constant in front. So just making it a bit easy, I'm going to take 2 sine 60, and I think they all have x. This has an x, this has an x, and this has an x out of it. I don't, actually, you know what? I'm not going to do that. I'm going to take the derivative just as this. So if this is the area formula, the derivative set to 0 will give me the max function. What's the derivative of this? It's just 1. So I'm going to get 60 times sine 60. What's the derivative for the next one? It's minus 4 sine 60 times x. And what's the next derivative? It's 2 times sine 60 times sine 30 times x. And to see that, this just has a 1 over it, and the x disappears. This has a 2 over it. It multiplies by the minus 2, and it gets reduced by 1. The sine 60 is just a constant. And it's the same. That's why you only have to multiply it once here. Same with this one. This just goes down front, and that gets reduced by 1, and these are just constants. Great. If I set that to 0, it's quite solvable, right? First of all, this is just a number, so I'm going to just get rid of it and send it to the other side. It becomes minus 60 times sine 60. I'm just going to leave it in sine 60s for now, and it might become clear. So I'm left with this, and so out of this now, probably a good idea to extract, let's extract a 2 out of it, a 2 sine 60. Okay. If I factor out a 2 out of it, I'm left with minus 2 x plus, that goes out, that goes out, 30 sine x. Okay, great. I have something which is just a number multiplying this mess. So I'm going to divide it out on both sides to get rid of it. And thus why we didn't get rid of the sine 60. Here the sine 60s cancel out. I'm just left with 60 divided by minus 2. Minus 6 divided by 2. Minus 30. Great. Now I'm left with minus 2, and actually, technically I should have factored out the x here. But let's factor out the numbers. Yeah, let's just factor out the x. If I factor out the x, I'm left with sine 30 minus 2. Those are just numbers multiplying my x. So I'm going to divide by it on both sides to get rid of it. Which means that the derivative, when set to 0, is x is equal to this. So I just need to take sine 30. Oh, sorry. It is just minus 30 divided by this. Oh, but I don't know. Yeah, it's going to come out as negative. So if I take sine 30, you're going to discover it's like a half, or I think it's a half. Yep. Minus 2 down below. So it's minus 1.5 down below. And you're going to divide it by 30, negative 30 by it, but I'm just going to do this and hit the reciprocal. And you're going to get out that x is equal to 20. Once you have that, and you realize that our original thing said that x plus y is equal to 60, you quickly discover that y is also equal to 20. Therefore, to maximize this area, which then gets multiplied by 5 no matter what, x must be 20. 20, 20, 20. Here, here, and here. And then determine the dimensions. Yep. And that's how you do that one. And as much as I've botched the other ones, that one's just a matter of knowing your geometry. And the train ones, the technique I did was right. I just kept screwing up the numbers. Looking at this one is interesting, and I just want to touch on it. That you just have to realize that you're going to need 2 numbers to solve stuff. And the math of this is hard, but the concept is not. So you have a graph here that's a parabola, and the parabola is going through 3 zeros of vertex. And they're asking you its proximity to a point over here, which is obviously in perfect line with an x value over here. So we could determine that. We might mistakenly believe that's the shortest distance. However, the parabola actually goes wider pretty quickly. And you'll discover that this line here, and how do I know that? I don't. Except that I know that I can set my search for what is essentially, unless it's a perfect line, and even if it's a perfect straight line, I'm going to discover it. I can just call this my, my goal. Let's call it my h. And I know from my Pythagoras that if I do a straight line out from here at 90 degrees and a straight line down, that this distance here is my delta y, my delta x rather, between this magical point that I'm searching for and this y. And this x. And then I also know this height is my delta y from this magical point here down to that y. Well, I don't know my x on this one, and I don't know my y, except that I know my y can be expressed in form of x like this. If I set this triangle up more visually like this, and the point I'm looking for is the green line, I quickly discover that this length is the difference between the x, so that's x from this point, x minus, sorry, the x value of this becomes x minus, what's the x of this one? Minus 3. What's x minus minus 3? X plus 3. The difference here becomes the difference in our y values. Well, that's the difference between this, that's my y value of this one here, and always is, minus 3. Okay, now you could expand it if you want, and actually you probably will have to, but essentially that's my delta y, and that's my delta x. And I know to figure that out, the hypotenuse is going squared is going to be my delta x essentially squared plus my delta y squared. If I was to get rid of this, it's also equal to the square root of all that. Gets complicated, doesn't it? So, since I know that this is my delta x squared plus my delta y squared, and that's the tricky part, is remembering this is squared, you will discover that the first derivative of this, set to 0, is how you solve it. The problem is the first derivative is going to be tricky. So, and it's probably going to be a trinomial. How do I know it's going to be a trinomial? Because of this situation here. I even have x to the 4. Okay, so it's going to be tricky. Because this is going to make that x to the squared, that's going to make that x to the squared, and ideally it would get square rooted and become x to the squared again, but the derivative, not so. And that's because the derivative of this whole thing, let's see if I can do it like this. This might work. Yeah. There we go. Can be expressed as x plus 3 squared plus, and we might as well solve this a bit, x squared minus 6x plus 9 minus 3 plus 6, all of that squared. So that's the resolved interior here. And it's all to the power of a half. So let's get rid of this. Hopefully I get the math right on this, because where you're going to make a mistake on this is obviously the math, right? Now the nice thing about derivatives is I'm going to be able to ignore the bottom once I solve it. So what's the derivative of this? Well, chain rule says it's this, and that's going to get reduced by 1 times the content. Okay, so what does this mean when this all goes down to the bottom, has a minus half? It means it all goes down to the bottom, and it all has a square root. So that's on the bottom. Also on the bottom with it is this 2. Where'd that 2 come from? That's what that half is. The 1's at the top, the 2's at the bottom. Great. Now all I have to do is take the derivatives of the content. When I take the derivatives of the content, it might help to just expand that so I don't do the chain rule over and over again. The expansion of that is x squared plus 6x plus 9. Now I can just do normal power rules until I get to here, and then I have to do the chain rule. So for now, let's just put this aside. Okay. Because it's really not going to play as much of a role. We can get rid of these brackets now, because that's what the chain rule did. The derivative of that is just 2x. The derivative of that is 6. This is gone. And this one, oh, remember that it's plus, so plus. And then this one, we need a bracket again, because it's plus 2 times the content. That gets lowered by 1 times the content, the derivative of the content. The derivative of the content is 2x minus 6. And that all has to resolve before I can add it together. That's the tricky part, really. So, I don't know if I'm going to go through it, but you're going to end up with quite a complicated thing where you can easily make a lot of mistakes. So that's this number gone through it. And that's this number gone through it. Just make sure, oh see, I made a mistake already. That's a minus. And then now we've got to multiply everything by 2. Why? Because of that. This 2 came from that. So we get 4. And here's where you can really screw up. You get minus 24. It doesn't help that I do chicken scratches. That's why I encourage you to have nice orderly writing. Plus 24x. It's easy to get some of the x cubes wrong, right? Very easy. Let's try to write that a bit better. This becomes minus 12. That becomes plus 72x. And that becomes minus 72 number. Okay, now I can add it all over here. I got a 2x here, 24x here, and a 72x here. So that becomes 76, 96, 98x. So let's write it just here, 98x, which means I can get rid of that. I can get rid of that. And I can get rid of that. Great. I got the 6 here. I'm going to add it to my minus 72. Minus 72 plus 6. Minus 66. Great. 4 cubed, good. Minus 24x squared minus 12x squared. Get minus 36x squared. So rewritten. Here it is. Now here's the problem. When we set it to equal to 0, solving it is a pain. We cannot use a factoring system. We have to go back to our old school and see if there's a trinomial setting that can factor into this to produce a factor. Now there is in university a quadratic function for cubics, but we're working with what we know. So when I put 1 in here, so I'm doing, what's factor theorem? It's when you just start figuring out values of x, and you're supposed to base it on this and that number, but that's so huge that I'm just going to start with 1, positive and minus, 2, positive and minus, 3, positive and minus, and you know what? If I didn't find it by here, I'd probably give up. What's the easiest one to start with? Plus 1. So when that's plus 1, that's 4, minus 36, plus 98, minus 66. So here you got 102 and minus 102, which means x is equal to 1 for one of the factors. Great. Since I know that if x is in this, the remainder is 0, I know that x minus 1 is a factor. If you don't remember this, that's factor theorem, which means that using long division, if I take the values 4, minus 36, plus 98, and minus 68, and just lower them, so 4, and then I got to remember I'm using plus 1 as the multiplier in synthetic division. That becomes a 4 over here. I add them, minus 32, times 1 is 32. And here we get 66. And don't forget that's minus 66 over here. And 66, and then indeed the remainder is 0. So we discover that it's 4x squared minus 32x plus 60. Now, at that stage, I can tell you that I would rather use my quadratic formula to figure out if there's any more factors. Because right now I have this as a factor. And remember, we set it to 0. And why do I have to figure this out? To see if there's any other factors where this can equal to 0. So that way I'll know if there's other maximum and minimums, because I'm trying to find the minimal distance. Right? And actually just knowing x is equal to 1, I could technically go back and just test out and definitely find, and I believe you're only going to find one value. That's the shortest. I mean, technically you could probably stop there, but I'm going to continue there. But knowing that x is minus 1 and knowing that this point here is this point, and that x equals 1 is indeed a maximum or min to the graph that we were discovering, I could plug 1 into there, and I get 1 minus 3 minus 2 squared, 4, and I know I'm dealing with the point 1 comma 4. So that means there's a point here that's the shortest distance, and I just need to find out that shortest distance. Well, what's the delta y here between 4 and 3? It's 1. What's the delta x here between 1 and minus 3? It's 4. This is going to be a sum of, this. It's going to be the square root of 4 squared plus 1 squared. That's Pythagoras' theorem, which is 17. So that length here is square root of 17. I would then put this into my quadratic function to see if it has roots. It does not, which means this cubic does something like this. It goes through x plus 1 and either does it dip up here or it does its dip down there before going through that. It only has one x-intercept, so cubics can have one x-intercept. There you go. So these things are solvable. They just take time. 3.4 is all about optimization. And generally you're going to look to maximize profit or you're going to look to minimize costs. And it's just a lot of work, right? And they're going to put up synthetic versions. And these are mostly for engineers and for economics. Economics actually does a lot of max-min. Read carefully because you can get really confused in what they're asking. This one asks a lot simpler questions than we believe. And I would strongly suggest almost everything. Put it in your Desmos. And set a first and a second derivative to verify your answers. And you'll be able to see various graphs and whatever. There it is. And obviously we're only concerned about cost from 100 onwards, because I believe they even put conditions on it. Yeah, see where x is bigger than 400. So they're actually only concerned about values way over here, where x is 400. So it's a good idea to figure out what that is. That profit is $750. So we know that at the start we're at 400, comma, 750. And that would be the amount of liters, and that would be the cost to produce it in dollars. I'm just going to get rid of my squiggles because they always end up being a plague. It's good to know. What is the average cost of producing 625 liters? Well, that you would just put in there as X, and you'd figure it out. I'm going to let Desmos do it for me. I urge you not to, because you're not going to have Desmos, but I'm just going to urge Desmos. So I get 1,125 is the cost. So that's the answer to that. Notice you can get confused. You say average cost and you start doing like average rate of change. But really, they're just asking you to plug that in, come up with the cost. Because this is the cost. the marginal cost CX and the marginal revenue. The marginal cost X liters is the expected change in cost if we were to produce 1 additional liter of syrup. Similarly for marginal value. What is the marginal cost at $12.25? So to do that, you're going to figure out the derivative, and then you're going to plug in this literage. Because marginal cost, they're telling us, is the derivative. Okay. It also helps to figure out what the actual cost is. It's $18.50. $18.25, $18.75 rather. Oops. And yeah, I expect you to do the long calculator version of it. On a test, you're going to have to be fast with your math, and you're going to have to try not to make mistakes. But that's just information for me. So how do I do that? Well, I take 75 square root of x minus 10. Okay, and you can either distribute, which will help you realize that this is the only thing we're concerned about. It'll just help you understand a little bit more what you're looking for. This is going to become irrelevant to the derivative. And this is the derivative. So you're going to get half, 75, and x is going to become negative half, and then we're going to multiply the content of x, which is just 1. Well, this negative half just means that it's 75 over 2 times the square root of x. And that's the derivative. And they're asking us to figure out when it's 125. So you plug in 2 times the square root of 125, 1225 rather. And generally questions are going to give you answerable stuff. So that becomes 75. Look at that, I forgot it already. How sad is that? I think it was 35, right? 35 over 70. And when you take the 7 point, yeah, just do the calculation. And that's the answer. That's the marginal rate. You might say, what is that? And go back to what you're measuring. That's the dollar cost per liter when we're producing 1,225 liters. Because obviously as this thing produces more, the cost gets less and less. And this one, they're asking you to take the derivative, which you figured out already, was 75 over 2x. And they're telling you that this is the marginal cost. And we were told that this whole thing is equal to marginal cost. Since they're telling us this is the marginal cost, we put that over here. And we need to solve for x. And how do you get x to a denominator? You multiply it. By the way, numerator, you always have to have x on the numerator, by the way. You multiply it on both sides by this. All right. It's going to cancel out here. What's 2 times 50.5? It's $1, right? So there's really no reason to worry about it. So we get square root of x is equal to 75. To get rid of this, we have to square both sides, and we get x is equal to 75 times 75. This is how many liters you'd have to produce. That's what they're essentially saying. How many liters would you have to produce to bring your marginal cost down? And really that's what it's about, is businesses do this all the time to figure out what's our best use of material in manufacturing. Because if you're going to build a factory with sewing machines, printing, press printing, silk prints, etc., and hire 20 staff, you're not going to make one t-shirt. You're going to make as many as you can to marginalize your cost. And at a certain point, your costs start, your marginalization can even go down. For instance, if there's not enough people to do the work, there's no point in buying 6 billion tons of cotton. And that's why today, especially, we have just-in-time economics where everything is based on a perfected system. It's why you see a massive economic crash when things get disrupted. So, for instance, when the virus hit, everything went into chaos because we don't have any room for error. And that's the only problem with a just-in-time economic system, is when it gets disrupted. Look it up if you don't know it. When disrupted, can kill people, can destroy societies. Not, maybe that's an exaggeration. But when you're making sure that every penny is used properly and suddenly there's a disruption in your system, business, at the very least, businesses collapse, as we're seeing with the airlines, the boats, boat cruises. Where else do we see it? Restaurants, right? Lots of restaurants are going under. And there's no easy solution to this, except that there's some, faults in the just-in-time economics model. So here they tell us this: some kid is learning. By the way, it always helps to analyze your graph to begin with, if you can. What's that going to be? It's obviously going to be a downwards facing parabola. Okay? And I can get a lot of information just by knowing my basic math. So I know already it has 0, 0 as one point and 20, 0 as another. And I already know his max thing's going to be at when t is 10. Because I already know the vertex, right? But they want you to use derivatives. But it helps to, in a test, to do this information so that you can just know. So he's a sociologist. That foreign language student has this learning capability, so obviously he can learn at his maximum efficiency there, and then he starts decreasing. And if he spends more than 20 hours, he actually starts forgetting things. How many terms are learned between the times t is equal to 2 and t is equal to 3? Well, that's just putting it in. At n of 2, you get 40 minus 4, 36. At n of 3, you get 60 minus 9, which is 51. So he learns between 36 and 51 terms. What is the rate in terms per hour which the student is learning at time 2? Well, for that we need to take the derivative of this. And I prefer doing this version because I like having my t-squareds in order. The derivative of this, of a parabola, is going to be a straight line. And we can see that there's a negative slope of this, so his thing starts at 20 and it goes down. And you might say, well, that's not a negative. It's only a negative slope on a certain point. You're right. Where it crosses 0, where does this cross 0? When minus 2t is equal to minus 20, when t is equal to 10. So on this side, he's maximizing his learning, and on this side, his learning is declining. So that's why he's increasing his learning here, and on this side, he's decreasing his learning. So now we just put 2 in here, because that's their question, and we get, first of all, I've determined where his maximization is, but when I just put 2 into this equation, I get minus 4 plus 20, 16. So he's learning 16 terms per time unit, which is hours. And that's how you would answer this. You'd say, what is his rate? His rate is 16 terms per hour at t is equal to 2. It's very specific to t is equal to 2. Later on, his terms will be decreasing. What is the maximum rate in terms of hour which the student is learning? Well, unfortunately, I answered it right there. Right. And it just helps understand the maximum rate. There you go. And you'll discover a lot of it's the same thing. And some of the graphs are hard to discover. I want you to pay close attention to this one. This is a line divided by a parabola. So normally a parabola would be like that. But if you're taking values like this, which are very big, right? They get very big. And putting it in a denominator of something, you're actually going to get something like this. It's going to hug, 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 hug. And at the x-axis, and I don't know yet. I've got to determine. I think it's going to be on this side. But anyway, it's going to theoretically, it's going to hug, hug, hug the y. It's going to bump up and then hug, hug, hug the y. And that's because these huge values of the parabola down here will far exceed this down here. It's important to learn what happens at 0, right? Where does this start? Because they tell us, you know, since time, it's only 0 onwards. Well, at 0, we get 0, right? Over. We've got to just make sure it's not 1. It's over 0. It's over 1. So we got a 0, 0 start. And you also have to be aware that if you took like 1, that's L of 0, you'd get 6 over 1 plus 2 plus 1, 4. So it's gone up, right? It's gone up. What is that? 1.5. So it's gone up. And then it also helps to realize, since we determine there's an origin start, and we determine it does go up, that when this is negative numbers, there's still some positive numbers in here. Okay? So it actually does this on the other side. And it's this little hump here that we're looking for, because we don't care about negative time. Right? So they want us, of course, to figure out the derivative of this. For that you need the quotient rule, or you could use the product rule too, but you're going to end up with the same thing. That would be as the product rule. And the quotient rule just says the derivative of f of x, which is your top term. Just put this somewhere. Is equal to 6 times your g of x minus your derivative of your g of x times your f of x all over your g of x squared. Now you're going to discover the denominator doesn't really matter as much. The resolution of this does. So obviously here you get 6x squared, right? Plus 12x plus 6. T squared, sorry. So that's the resolution of that. The resolution of this is 12t squared plus 12t. But all of it minus, right? So you're going to get minus, now that we can get rid of this bracket, minus twice. Great. 12t minus 12t. 6t squared minus 12t squared becomes minus 6t squared. I can factor out a minus 6 up top, and I'm left with t squared plus 1. Now when I set it to 0, this denominator doesn't matter. For the same reasons I've explained before, that only the numerator dictates a 0 value. The only exception is when that 0 value also would create a problem with the denominator. Okay. So we have this, and we're going to solve for t. So I'm going to just divide both sides by minus 6. You can see it just disappears. We're going to move the 1 to the other side now. It becomes a Oh, here I might have made a mistake. -1. Yeah, I believe I made a mistake somewhere. So, mistakes happen. So the derivative of this one times g of x is going to be 12, 6. Okay. All minus the derivative of 2t plus 2 times 6t, which becomes 12t squared. So I still think I got it right. Oh, you know what it is? It's the -6. 12t squared plus 12t. Yeah, I still think I got it right. So I got -6t squared make sure, yeah. These cancel out. Plus 6. If I set that to 0, there you go. Here's where I made my mistake. I forgot that that I should just set it to 0 right here. Because when I siphon this out and divide it, I'm getting rid of a minus that shouldn't really be gotten rid of. So I get rid of -6t squared is equal to -6. T squared is equal to 1. Therefore, t is plus or -1, but we know we don't have -1. So plus 1, which means when the time is 1, we achieve our maximum level of antacid, which we already discovered was 1.5. Determine LT for the value you found. Yeah, we just did, just to make sure. 6 over 1 plus 2 plus 1, 4, which is 1.5. And what kind is it? It's 1.5, we don't know the amount, antacid in the stomach per minute. Okay, graphing calculator. Yeah, it's going to go down. Since that's the peak, it's going to go down. Simply because I know this becomes huge. Okay, well, I guess we'll graph it. It's always a good idea to graph it anyway. 6t over t squared plus t. Okay. I can't remember if it was, see it? 2t. And if I'm going to do that, I got to switch everything to that. Yeah, I don't think it's going to let me. There we go. Yeah, we'll skip that. Okay, let's go home. There we go. And sure enough, right there, that's the peak. And they're asking us what happens between 2 and 8. T. There we go. And it's only undefined because I didn't put an equal sign there. But you can see a gentle decline. And why not just between 1 and t, because that's the peak, right? And notice it's leveling off. It's going to hug the asymptote for as long as it can. This graph can never reach a 0 value. So getting rid of the limitations here, notice what happens here. You might ask yourself and say, Peter, I thought you said it's going to continue on, but there is indeed a 0 value possible here. Is there a 0 value? Yeah, there's a 0 value possible. So it's when t plus t squared plus 2t plus 1 is equal to 0. When can t squared be equal to minus 1 plus 2t equal to minus 1? Let's see if we can figure that out. When can we get a 0 value down here? When that's equal to -1. Well, and actually you would just factor it. You just determine if there's a factor here. And suddenly you realize that when this t is equal to -1, this whole thing becomes 0. So there, my bad. It also helps to check to see if there's an asymptote. And we can see there is at this value. Okay. If this had been a bit higher, let's see, there we go. Yeah, it can't create an asymptote. And that's because there's no value of this that can exceed that. Or match that, I should say. See? But probably anything below 1. 1.1 would be fine. Yeah, see 1.1 has its limits, it dips down a lot. And the more I get close to 1 there, the more it sort of becomes an asymptote, except eventually it will have a limit. I imagine that limit here is ridiculously huge. It is. Well, maybe that did create an asymptote. No, I don't think it did. It just was one I couldn't reach. See, this is the kind of thing that just fast forward. Oh, look at that. There it is. See? It looked like it was going to go on forever. And then, of course, as soon as I get below 1 here, we're going to have an asymptote. That's because these can exceed that or match that and create an asymptote, essentially. Interesting stuff, I guess, for me, maybe not for you. Part B, so obviously they get harder, and they start putting the values in spots that aren't necessarily useful, right? So we'll go to that. Get bigger, and crop. So an operating cost for an airplane. Look at the graph. We're dealing with something that doesn't have an asymptote, but clearly, when height is 0, we have an asymptote there. Fortunately, they make our height between 1,000 and 20,000. Our question is there an efficiency there? And you also have to be careful to sort of have an idea of where that is and where that is, because it might be higher or lower than your value. So again, I'm going to let you do a lot of the calculation, and I'm going to walk through the calculation, but I believe this is a better use of our time, and I urge you to use Desmos as a tool to verify your work, not as just I'm going to get the answers. And that's because if you do just use Desmos and you come to a test, you're going to be screwed. So we know right away it's going to be in 1,000. So I'm going to make my Y grid step of 1,000. No, my X grid step of 1,000. Maybe step of 2,000. And I'm going to put my Y way up from like 10 to 200, step of 10. Okay. So it wasn't able to do both, I guess. So since this is more important, 40,000, and I think it was 1,000. There we go. There it is. So there's the actual graph, and that's the one we're concerned with. So if I do that, so that's what we're concerned with. But right away, you should determine what your F of 1,000 is. you should make sure your numbers are right first. 4,000 plus x over 15 plus 15 million over x. Okay. And your f of 20,000. And you just do a rough calculation just to see roughly where these lie, right? And I put the domain wrong. And if you don't have time in a test, you know, try a guesstimate. You can instantly say, okay, I got 4,000. 1,000 divided by 15 is kind of like divided by 10 and divided by 20. It's somewhere between 500 and 50 and 100. So I'm going to go 75. And I'm going to go, what's 15,000? I'm going to knock off 3 zeros. And it's plus 15,000. And right away you can say, okay, that's 19,000 and something. Close. And you can do the same thing with 20,000. Or you should be able to anyway. You should be able to say, okay, well, 20,000 is, we got 4,000. 20,000 divided by 10 is like 3,000 divided by 15. No, yeah, 3,000. And then this, I got 4 zeros, 4 zeros. That divided by 2 is 750. So we're talking about 4,000, 3,700, around 7,750. So clearly I did a little quick error there, but it gives me a rough idea, right? So I can see that it definitely is high here and lower here, and that helps. So I know it's here and somehow gets here. Doesn't do anything in between. And that's the cost, right? So this y value is the dollar value that it costs to fly at those heights. Okay. Determine the height at which the operating cost is minimum. So that all comes down to a derivative. Right? And you're going to set your derivative to 0. Sure, for some of these questions you don't have to go to decimals. Just realize that this is the same as that. And that this is the same as this. Also realize that when you take a derivative, numbers are going to disappear. The derivative of this is that. The derivative of this becomes a negative in front of the 15. And this becomes to the 2, so it goes down negative 2, so it goes down there like that. And now you might say, well, how do I set that to 0? And you have two options. And this is C prime now. Mark, always make sure you know what you're calculating. And we're going to set that to 0. So you have two ways. Put it on the same denominator. In other words, multiply this side by h squared over h squared and this side by 15 over 15. So that you have 15h squared down here, and then just set the top to 0. Or you can do it this way. This is minus this whole number, so I'm going to add that number to that side. That's a plus now. Okay. And probably extra step there, but sorry. So I'm going to multiply it by h squared on both sides. So now you're left with essentially this, h squared divided by 15. So now you're going to multiply that by that. And you're going to take the square root. And you're going to get the height. And since they said also find this, whatever height you get, you must plug back into the original formula. So we're going to take 15 times 15 million. And we're going to take the square root. So that's the height. And ask yourself, ask yourself, is that between here and here? Sorry, here and here? And yes, it is. And then you would calculate your height. So if you're going to do it long form, it's going to be this. What's 15,000 divided by 15? 1,000. So far I got 5,000 plus 15 million divided by 15,000. So 3 zeros off. 1515 plus 1,000. So my height is going to be, my cost is going to be $6,000 per height, so per meters at 15,000 meters height. So always answer this. The height where operating cost is minimum is 15,000 meters, and the cost at that height is $6,000 per meter. No, it's not 16,000 per meter, it's 6,000. That's how much that would cost for that particular height for cruising dollars per hour, so I guess it is per hour. Costs you $6,000 per hour, and that's the height you should fly to maximize your fuel. Minimize your fuel, sorry. Maximize your fuel efficiency. Boop, boop, boop. And they're all the same thing. You just have to understand, what am I measuring? Rectangular, two kinds of fencing. So in this case, they're giving you a scenario where one side of fencing costs a little bit different than the other side of fencing. Oops. The other side of fencing is going to cost you slightly different. And because of that, you're going to label this X, right, and this Y. And they're going to tell you $6 per meter, while the other two sides cost $9 per meter. What are the dimensions of a rectangular lot and we fence for a cost of $9,000? Well, it's still the same thing, except this time, let's call the shorter one $6. So you get 6y plus 6y plus 12y, and the lot of the greatest area, so we're going to work on the area function. Sorry, so you still get this. You still get, sorry, x plus y plus y is equal to a perimeter, right? Except that that's a good question. I believe you have, because it's $6 per meter and $9 per meter, not per meter squared, you have to apply it here. So you're going to get, let's call x the more expensive one. So you're actually going to get 18x plus 12y is equal to your perimeter cost. Right? Because the more fencing I use on the expensive one, it's going to drive up my cost. So I suspect it's going to affect the shape quite a bit if I'm going to achieve maximum area. Now area is x times y, and I do not believe that's going to be affected by the cost. But you do need to have a version of y that you can fit in. And since you know that your cost here is going to be equal to 9,000, you realize that your y can be, and this is called a weighted, it's essentially weighted, where one thing affects the other because it's got more weight to it, is actually really common. It's how your marks, for instance, to calculate your marks. If your exam is worth 30% and an assignment is worth 2%, you want to get more, you want to make sure you get the exam right. So you could divide this out if you want. And this is 6, you get 2, you get 3, so 3 over 2x. So that's my y. And now I believe, and we'll just, I believe that you do not weight y for the area because of that. Weight has nothing to do with the area. It's just the dimensions. Good question. Should it be 9x here or not? Let's see what we get. First of all, let's see what we get with this, because I know this is true. It's going to be 18x plus, actually we'll put it in terms of this. And we're going to do x of, we're going to set that to, what did we say it was, 9,000? Helps if you actually don't destroy the question. Let's see what it says when I set that to 9,000. And this is the cost you get. The y value is 747, so you have to set y 747, which is at the cost. That's going to be the total cost, I think. It's a good question. I think I kind of botched it, but we'll see. Let's see what kind of graph I get for this. X times that. Okay. Let's skip that and just see what kind of graph it is. Right. Let's see just right away where the derivative is. So right away I think I have a botched thing. It's telling me there's no max area. So I believe, oh, that doesn't help. There we go. Well, we'll see. We'll see. So taking the derivative of that, if I expand it, I get 750x minus 32x squared. Taking the derivative of that, I get minus 6 over 2, which is minus 3x, plus 750 is equal to 0. So x is equal to 250 once I do it all here. And then when I put x into the 250, so right there I've got to go back to this formula. Yeah, I can set it for this. It was, again, I should have just kept it as is. Yeah, we'll solve it for 250 right up above. Yeah, that's going to give me the area though. And now I need to go back to the original formula that says y is equal to 750 minus 32 over x. And for x I need to put in 250. You get a y 375. obviously the y is going to be cheaper. And if I did my calculations correctly, this times $6 plus times 2, and this times $9 times 2, because there's 2 fencing, should equal 9,000. So let's see if that's true. So that's 4,500 here. I'll bet you the cost is going to be a square. But yeah, it definitely is going to be. Yeah, that's these two sides and these two sides both cost 4,500. And when you look at that algebraically, it makes sense. For me to achieve a $9,000 cost, I should make this 4,500 cost by 4,500, right? It's like a perfect square of costs. And then I have to divide that by the actual cost, and I probably could have shortcut it like that and discovered my actual length is affected by the cost, and my actual length is affected by the cost. But your cost by cost should be a perfect square, which makes a lot of sense. And I believe I got that right there. Because area won't be affected by that cost. Area is area. And sorry for stumbling. Sometimes I'm not a big fan of the economic. I can see its value though. Economic calculus. So we got a guy who's got 50 apartments. When the rent is $900 per month, all the units are occupied. For every $25 increase in the rent. So start with this. What is it when it's fully occupied? It's the same as 5 times that, but it's really 900 times 50, which is equal to $45,000. So since this is cost and this is occupancy, we would break it down like this. For occupancy, it's going to be 50 minus, so we're going to lose people. Actually, let's start with rent. For every 900 that we increase by 25x units, we're going to lose our 50 people minus 1x. Because for each $25 increase, 1 unit becomes vacant, so we're going to lose a tenant. So then there's a cost, right? They've added on this operational cost. Is equal to $75 and repairs in each month, but it's times the units, which will also be affected, right? If I'm going to make my operational cost related to this, so this is going to be my total profit, but I always have to operate my operational cost. How much rent to maximize profit? So profit is always going to be revenue minus operational cost. So it's going to be this, which is a multiplication, which is clearly a parabola, minus that. So I have to take the derivative of that, obviously, to find out when this achieves a maximum. That maximum will give me my x value. Don't be aware though, my x value is each, since they're asking how much rent should I charge, that x value should go into here to determine the total rent. My x value is not going to give me the rent. It's going to give me the amount to punch in here to determine the total rent. So when I'm done, that doesn't matter. So if we're going to expand this, I'm going to start with the x squareds first, actually. What would this be if it was times 100? It would be 2,500. So what's half of that? And this last number, 50 times 90, plus 4,500. 45,000 rather. These makes plus 350. This is still minus 25x squared. And this is plus 45,000, which you're going to see is going to be affected by the next part. So that's that left part. that's my revenue. And it's good to hang on to your revenue model. What would this be times 100? It'd be 7,500. So what's half of that? So we have to determine that minus that. And we have to determine that plus that. Great. We now have a profit. We now have a profit model. Now we're going to take the derivative. And that's where writing is key. That's 425x. Okay, so I got two pluses in there. That's why I'm screwing it up. Okay. There we go. Take the derivative. The number's not going to matter. Set it to 0. So you get 50x is equal to 425. Therefore, x is going to be not a perfect number, which makes me think I just did an expansion wrong, because these questions like even numbers, right? So what I'm going to do is put that into the model and get it to expand it for me. Actually, I'm going to get it to expand everything. Notice that I should have kept my operational cost too. So it's going to be minus 75 times 50 minus x. Okay, I'm going to get Desmos to solve that for me. Actually, I'm going to get Symbolab to solve that for me. Even better. Let me get it to expand. Hopefully it expands all of it. Who knows? I might be right. I should actually check the answers. Yeah, I got it. So I got it right. Good. So good to know I got something right. So when I figure that out, I get $8.5. And then when I put that into the rent formula right here, 900 plus 25 times 8.5, I get this. He should be charging this to maximize his profit. And by the way, when he does, he's only going to have 50 minus 8.5. He's going to fluctuate between 41 to 42. And technically, he's going to average out at 141.5 units. He's always going to have 8 rooms empty. So he should Airbnb those. I should pull up the answers to make sure that I'm getting these. It's pretty arrogant, but if I am making a mistake, it's an arithmetic mistake. The techniques I'm using are accurate. Let's see. 13. values. Do I have them all there? Yeah. And where are we here? Are we 4.3? I'll pull that one up. How come you didn't stay there? That's annoying. Four point three, 4.4. Better have stayed up. Yeah. 4.5 and 4.5 in review. Okay. We are in what section? 3.4. That was smart. Stupid. 3.4 is there. And where else? I think that's it. Where's 3 in review? Oh well. I think I'm missing my 3.4, but anyway. Get rid of that. Gonna get rid of that, that, that. What questions were we doing? We were doing 1 through 7. Yeah, okay. So their answer here is because you can't have a half person. So there's 2 answers for the rent, which kind of makes sense, right? Ooh. So yeah, that's what we got for X, isn't it? Oh yeah, we had to figure it out based on its non. That's what we got. That's what we got for this plane as well. Okay. Yeah, so far so good. We got all the correct answers, it looks like. I think we got one wrong. I think this is wrong. Didn't we get like 11,000? So we might have gotten this one wrong. I can't remember. But so far so good. We're doing pretty good. All right. Sorry to waste your time. Always fast forward when I start to ramble. Just hit the double speed. Buses, it's going to be the same thing. So we're going to do, and you'll notice these get monotonous, but I understand. The point is you're trying to get proficient enough for a test, right? So here we got 10,000 people, and the company has space to serve more. The cost is 20 bucks. So normally they charge 10,000 people times 20 bucks, and they make $20,000, right? Or $200,000. So that's normally their thing. So obviously they're looking at a fare increase by 50 cents, and 200 people fewer will go. So you're going to get, when you have 10,000 people, sorry, at 20 bucks, they're saying for each time we increase that by 50 cents, and that's why you got to do 0.5 if you're dealing with dollars. We're going to lose from our 10,000 people. We're going to lose 200 people. And that right there is the model. What fare should be charged to get maximum revenue, given that the operator must have at least 130 to cover operating costs? So I believe, technically, we need to subtract $130,000 in operating costs, because the right is my well, it's interesting they don't ask for max profit, because normally profit is going to be revenue minus costs, but they then go on what fare should be charged to maximize revenue. I believe I'm supposed to account. Let's put that in there. They wouldn't have said this if it didn't matter. So when I expand this one here, I'm going to expand the x squareds first. Okay, minus x squared minus 2,000 minus 4,000x plus 5,000x, and then what's the last number? plus 20, 200,000. So you'll notice our max cost is always at the end there. And don't forget that this is a squared. Now I'm also going to include this because it's going to affect, but we'll do one with and we'll do one without. And in this case, I'm going to make sure I keep both. Okay, so this is my profit, and I don't know if they're looking for my profit or just my revenue. Okay, but I'm going to keep a copy. I'm going to keep it right there. So obviously to find max, I've got to take a derivative, and I've got to resolve that too. So I get minus 200x minus 4,000. Oh, well that's good to know. This here is plus 1,000. So I could have shortened that, right? And of course the derivative, it's not going to matter. The numbers aren't going to matter. So I'm not going to worry about that for the derivative. I set that to equal to 0. So x is equal to 5, which means, what are they asking? What fare should be charged to maximize the revenue? So this is where I should have kept it in. The fare is 20 plus 5x, right? Plus 0.5x. X is 5. So that's 20 plus $2.50. $22.50. Notice that the operational cost and the total revenue cost here didn't impact on my fare charging, which is interesting. Which means to max profit, I really have to look at my fare increases versus my customer base rather than my operational costs, which it's interesting. Let's see if I got the right answer though. Right? Number 7. Yeah, I did. 22.50. Okay. And notice the ones with C are going to be a little bit tougher. Ooh, wow, 11. Okay. Create a new one here. Come on. Take that. Now, I don't know if I'm going to do all these, especially the ones that repeat. I know I say that each time and I end up doing them, but still. I probably just end up giving you the formula. So we've got a fuel cost for ship, 1/2 the cube of the speed. Oh, they're just not even doing that. So, okay. So fuel based on speed, we called speed, is going to be 1/2 the cube root of speed in knots, okay, plus 260. So we're going to call that cost, we're going to call it cost. It's based on speed. Okay, rewritten, that's this. Where x is speed. So technically that should be this. Okay. And then they say find the most economic speed to run the ship for 500 nautical mile trip. So that's a mile trip. So that's a distance. So I believe that's speed. 500 knots, by the way, is 500 nautical miles. Sorry, knots is a nautical mile per hour. let's find the derivative first for s. Okay. What's interesting is that's a mileage, that's a distance, and that's a speed. They haven't given me a time, except per hour. So to know how long he takes to do this, I would know that, oh, they want the most economic speed. So they're going to want to know s. But, well, we'll try it one way. So I can find the most economic speed taking the derivative, right? So I get 1 over 6. That's going to become the square cube root down here. I'll let you figure out how I came up with that. And times the derivative of speed, right? Which is just 1. So this is the formula. But to know speed, I have to know time. So if I set that to 0, right? The answer to that is never. Half the cube root of the speed measured in knots. And I'd have to know the speed or the time. Let's see what Desmos says about that, okay? Half the x to the power of 1/3, that's the cube root, plus 216. Right? Let's get rid of all this. And see what you get me. If anything. Helps if I turn it on. Right? I don't think there is a max. I mean, is it? Does it go down again? I don't think so. What do they say for that? So this is cheating now. I'm officially cheating. Well, they give a speed. They say it's 6. Interesting. Let's take f of 6. Let's take f just beyond 6. No, it went up. Let's just take below 6. It went down. That's going up though. So I made an error in the equation then. And that comes about when you don't quite understand what they're asking. To me, I would need to know the knots. I know the 500. So knots is based on nautical miles divided by time. So I guess I could do this. I know it's going to be speed here is going to be 500 over t. Let's see what happens there. Okay. Nope, same issue. Let's see if it has a derivative spot. Saying no. So somehow I got the equation wrong. 1/2 the cube. Oh, the cube. What an idiot. See if there's a purple now. No, still no purple. And that's, x would be time. Let's just do x as that. And still no purple. Oh. No, still no purple. Maybe just reread the question. Wow, I'd love to hear the answer to that. For some reason, this one's stumping me. So it could be this, especially since I screwed that up. Sorry. The cost is going to be based on 1/2 the cube of speed. It's called velocity. Plus 2/16. Velocity is distance over time. If I take the derivative of velocity based on, or derivative of cost based on velocity, I get this. Okay. Yeah, I'm still missing a variable, because if I set this to 0, it's still 0. So clearly, there's something going on here. Maybe they had to go, I don't know. That one's got me. Someone wants to comment. Go ahead. And let's keep going. I hate being stumped by that, because I don't really think it was that hard. I just think there's a key bit of information I'm not seeing. Okay, so here we have this stupid rectangular cistern. Reinforced concrete. Okay, the interior length will be twice the height. Okay, let's start with that. So let's start with what we know, right? And that's this and this, and that L is equal to 2H, which means I can interchange them. And they're dealing in cubic, so we got a volume. This says quadratic function. Rectangular cistern. So I think I'm just missing what interior length is for them, because we're missing this dimension here. Is that an interior length? Let's call that interior length, and we'll call this something else, width, I guess. And we also know that width times length times height is 20,000 meters cubed. We also know that if this is called the base, that's going to be $40 per square meters. All the walls are 200. And the roof is going to be 200. So that means the roof up top The roof is W by L. Roof equals W times L. Base is W times L too. Except the roof is going to cost, the roof is going to cost 200 and the base is only going to cost 40. And then there's 4 walls, and those are all, 2 of them are W by H, 2W by H, and 2 of them are 2L by H, and those all cost 100. Okay, so the total cost is equal to 200 WL plus 40 WL plus 100. Yeah, we might as well expand it. 200 WH plus 200 LH. And you can see that the only ones we can add together here are 240 right there. However, we can also replace L, wherever we see it, with 2H. And we can also replace our W. We can also replace the 2H here. Right. So that's 2H squared, which means we can also replace our W with 20,000 divided by 2, which is 10,000 over H squared. Fair enough. Clear that these will cancel out a little bit. Okay, it's clear that this is going to be equal to that times 2. Okay, this is going to be equal to this. And this is going to be equal to 400 H squared. Once I figure out H, I'm going to be able to figure out everything else. So I must take the derivative to maximize my H. F off. Keep in mind that's H to the negative 1 and that's H to the negative 1. So you're going to get minus 480. Ooh, that's a big number. Missed one. Yeah. Over H squared. Minus 200,000, no, 2 million over H squared plus 800 H. You have 2 options. You can multiply this by H squared to get it all on the same thing. And I think I'm going to do that. get h cubed here. That's all over h squared. I'm going to set it to 0. So I'm going to get 800 h cubed is equal to this plus that. So that's 6 zeros, and that's 6 zeros to there. So I get 6, 8, and these 5 zeros. And it's all going to be divided by these 2 zeros and this 8. Might have made a mistake there. Who knows? So, although it says to the decimal place. So I get 68,000 divided by 8. And I got to cube root it. So I get that as my height. Which is not what I got. Get that as my height. There we go. So that is equal to my height. I also know that I said length is equal to 2 times height. Right? Didn't I say that in the beginning? That's where I should have kept this. So length is this. And since I know that width is equal to this, length times height times width times 20.4 times 40.8 will be equal to 20,000. I can just say that width is going to be equal to 20,000 divided by 20.4. Now, even if I did a mathematical mistake here, the technique is correct. Okay? And it's starting to look like it based on these numbers. So that's that. So I'm left with W is equal to 24 meters probably. Height is equal to 20.4 meters, and length is equal to 40.8. Very confusing question. I hope to God I got it right. What question was that, by the way? Number 9. Looks like I did. Whoops. There we go. Bingo. 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 Okay. Good to get that one on air. Oof, but you can see how long it takes. If you can master these, you're probably going to do fine on the test, because he's going to ask maybe one extraordinary one for extra marks, and that's it. These cylindrical tanks, again, they always puzzle people for no good reason. They're not too bad. Just remember that a cylindrical tank is simply 2 circles. Simply 2 circles at either end, and when you unravel, so the areas for that is pi r squared times 2. And when you unravel it, you end up with a height, and this whole length is the perimeter of the circle. So you get 2 pi r is the length. The end pieces are twice as expensive per square centimeters as the walls. Find the dimensions to the nearest millimeter to make 1,000 can. So for a cylinder's volume, it's simply the height times pi r squared. So volume is equal to height times pi r squared. They give me the volume, so I know I'm going to be able to find a version of that works. Okay. and find the dimensions to the nearest to make 1,000. So I also know that these are twice as expensive. So if I was going to add up the cost, I'd say dollars of the top. So that's twice as expensive for the top, which is called $2. So it gives more weight, and there's two circles, so it's pi r squared again, plus the height times 2 pi r. And that's not as expensive, it's not twice as expensive, so I'm just going to use the 1 in front of it. Okay, now it all depends whether I'm solving to height or to radius, and personally I think I'm going to set my height is equal to 1,000 over pi radius squared, which means that everywhere I see h, I can replace it with this. Okay. Now that is going to be the total cost of my cylinder. And I've given more weight over here. So I get 4 pi r squared. These cancel out. These cancel out. And this multiplies. So I get plus 2,000. Essentially times r to the minus 1. Okay. Taking the derivative to find the maximum area, I get 8 pi r minus 2,000 over r squared. I'm going to put it all over the same thing by multiplying this by r cubed, so all over r squared. So I'm going to multiply this side by r squared over r squared to get it all over the same thing. Once I have it all over the same denominator, I can just forget about the denominator, set it to 0. So obviously this is going to be equal to 2,000 divided by 8 pi. So at this point I will take out my calculator and take it divided by 8 and then divide it by pi. And I get this. And I'm going to take the cube root of that. And I get this, 4.3. And then you're going to go back to your question. Meters is the radius. You're going to go back to your question, and it's going to say, find the dimensions to the tiers to make this. Well, radius is that. So diameter is 8.6. And I know that my height is based on this here. So it's going to be 1,000 divided by pi. And it's going to be divided by 4.3 squared. So I get this as my height. So h is equal to, and I think they just want it to 1 decimal, right? To the nearest millimeter. Okay. What we were working on. We were working on centimeters. Yeah, so the first decimeter. So this is what I got. Let's see if I got it right. Nope. Oh, wait. Yep. And by the way, I said meters, but of course it's in centimeters. Boom. And boom. Good. That's good to know. All right. Going on. Damn neighbors are operating in a successful bake shop. I'm going to report them for selling goods during a lockdown and have them shut down, so their costs and revenue are 0. And there's my answer. Or I'll have to do all this calculus. They buy the cakes from a supplier, so they operate a successful bake shop. One of the specialties is a very rich whipped cream cover cake. They buy the cakes from a supplier, $6, so they charge $6. They sell 200 weeks at $10 each. So, here's their profit so far. It's pretty clear to see that their profit is 4 times 200. It's going to be $800 per week. So, since this is the profit, sorry, the number, they're going to lose 7 cakes each time they increase the profit by 0.5x. Now, be careful here, because it's now 200 minus 7x times 6 cakes, because this number varies directly with this one. Right? Okay. So again, they're dealing in profit, so that's profit. Always profits revenue minus costs. That's costs. That's how much it costs them. So we would have to expand it. I like expanding my my x's first. So I get minus 3.5x squared plus 100x minus 70x plus 2,000, which really won't matter, minus 1,200 plus 42x. The numbers really won't matter. This is 30x here, plus 42x. And I just have to remember to put a square. Now let's take the derivative. Set to 0. I might have made a mistake here. I don't think so. Which means x is this, but careful. That's not how many cakes you're selling. It is the increase, so we know if we're going to determine price, we have to go back up here and determine that it's 10 plus 0.5 times 10.3 . And we get $15, and price of cake is $15.15, was it? I should not be multiplying. I'll just go with that. Oh, and you should also figure out how many cakes that is, because I believe, yeah, it'll make it below what they want. So then they're raising this price. So what that affects is this one right here, which is a shame. I wish I hadn't deleted it, because what that affects is this 750 will now change this minus 7x, which will become plus. So 750 now times 7. So you're going to get plus 52x now. Now, interestingly, the number doesn't matter. But right here, when you get minus 3x squared, you then get plus 100x minus 70x, blah, blah, blah. The number doesn't matter. So this 52 affects this now. So it's 82 now, 82x. And now, I'd be smart to keep all my numbers in case they ask something else, but the derivative of this now is minus 7x plus 82, which means 7x is equal to 82 when I set it to 0 here, which means x is now $11.7, which means the price is going to be right here, 10 plus 11.7 times x times 0.5. So 11.7 times 0.5 plus $10. $15.85. So now they have to increase their price to $15.85, which makes sense because their costs went up. Well, yeah, but here's the whole goal. If I can make more by working less and manufacturing less, saving time, it is always optimal, even losing customers. So that's great when you're selling cakes. And here's where it's not great. Pharmaceutical companies use this, and that's why you will see a drug go from $10 to $1,000 because they would rather sell to 5 people than 400. So when you're dealing with health, it's an issue, right? You could also say this, which happened in the 1970s. Ford Pinto made a car that exploded by accident. People died and sued, and they calculated it was cheaper to pay out the lawsuits than fix the car. So they kept letting people die. So that situation happens as well. And I think there's a couple other issues I could come up with that go on and explain it. Let's see if we got the right answers, though. That's when an economic model doesn't suit a real-life situation, right? Let's see if we got the right amounts, though. Oh, wonderful. I didn't even copy it. And I might have to stop soon, mostly out of frustration, but also because... oh, God almighty. Why don't you... Oh, Jesus Christ. Okay. Let's see if we got the right prices. They've rounded up. We got the wrong price here, and we didn't answer the question fully. So we got the wrong model. So we needed to adjust the model. So let's see if I just did a mild typo and just do Desmos to the rescue. So the formula is simply going to be in brackets 200 minus 7x times $10 plus 0.5x, all of it minus bracket bracket 6 times 200 minus 7x. Right? So let's see what we got there. We got some weird model. Is it giving me two values? No, it's saying 10 is the price. Let's see, maybe I got this part of it wrong. No, that should be the amount of cost to cakes as the thing declines. So saying 10.26. $2.86. So they're saying an even different value. Somewhere around there. Which means my cake cost will be 10 plus 0.5 times 10.3. Let's get rid of that. 1515, that's what I came up with. And then we had to adjust this. Maybe they're wrong. And they started saying, what did they start saying? That they would have to increase it to 750. And that affected my, became 11.786. 0.786. And suddenly my cake price jumped up. So I did a calculation error. So I had to put that in, and I did a calculation error because that's the answer from the book. So all I did was a minor arithmetic error there. This is the same thing that we've done. So it's a jewelry box. You have to figure out the dimensions. You have a volume equation, so you know length times width times height is equal to that. You know the bottom and the top will be the length times the width, and you'll know the sides will be the width times the height, times 4. Then you have to multiply the sides, 4 of them, by 30, so you're going to get 120, and you multiply the top by 20. It's the same thing. I'm not doing it again. If you want, what I'm going to do is tell you the formulas you have to come up with, in case that's your weak point. Okay? So we're going to do this one first, 12, and you have to use your imagination. What's the bottom? It's going to be a thing like that, right? And there's a bottom and a top, right? Because they've closed it. So there's another one. So there's 2 of these. So first of all, do length times width times height. That's the volume, is 4,000. So you have an equation there. That's one equation. You know that the top and the bottom cost 20. And we're going to call that length and width. So that means there's 2 of them. And there's 20 bucks of them. So that's going to be 40. So that would be an equation for the surface area of that. And that's what material cost is, the 2-dimensional cost, ignoring the thickness of the wood, to do it. So that's for both top and bottom. Then you have these sides here, called this new thing, height. And 2 of the sides are height times width. And 2 of the sides are length times height. So if you can't see that, then practice your sides more. So there's 2 like that, and then there's 2 ends like that. The ends are width times height, and the sides are length times height. So that is the total cost of the side. Now, fortunately, the sides cost 30 no matter what, so this is 30 times both of them. If you distribute that through, you get 60 times height times width plus 60 times height times width, which means the total cost of this box is this. 60 times height width plus 60 times length times height plus 40 times length times width. Now what's the problem with that? You've got 3 unknowns in there, correct? So one thing you can do is that you can rearrange this, but first you got to find one more unknown. Okay. Ah, there was the key right there. Square base, which means my length is going to be the same as, let's say, my width. So where I see length, I'm just going to replace it with width. So here, since that's the same dimension, it's w squared. And here, it's just a w. So wherever you see length, it's just a w. Because they gave a square bottom. So a square bottom jewelry box looks like that, right? And then it's rectangular after that. Since these are the same, I can just call it w, w. And just keep that the same because height is different. Height is this long piece. And then over here, instead of length, I can say w squared. Which means that everywhere I see height, I can replace it with 4,000 over w squared. So right there. Jesus. And right there. Just remember that it's 4,000. And you can see right away there's a cancellation here. And there's a cancellation here. There's an extra 0 here. And this is going to be 24. There's an extra 0 here. And this is going to be 24. And then finally, this is just that. Now, when you readjust it, that's the same as -1 plus to the -1. So that when you take the derivative, you're going to end up with minus 240,000 over w squared minus 240,000. I might have gotten this stuff right, over w squared plus 80w. And to get this all in the same denominator, you multiply it by w squared. So you get w cubed here over w squared, which means you can just make the top equal to 0. And once you discover w, you're going to discover that it's 80w squared is equal to 480,000. When I divide by 80 on both sides, get rid of a 0. You get rid of that. So 48,000 divided by 8. You get 6,000, and then you got to take the cube root. So the length is 18.2, width rather. 18.2, which means this box has an 18.2 by 18.2, and then to figure out the height, you just got to take 40,000 and divide it by 4,000 and divide it by 18.2 squared. And you get a height of 12.1. So height is 12.1. Width, or whatever we discovered at the bottom, is 18.2. So it's much wider, and we have to be very careful that we made sure the bottom was. I might have screwed up the cost when I did that, but we'll see. It's 12, right? No, we got it. $12.1 by 18.2. Check, check. Is this going to be any different? Probably not. The regular price is $90. Jesus Christ. And you usually sell 50. So now for every time we decrease the price by 1x, we sell 5 more plus 5x. So this one's pretty straightforward. Expand it, you get minus 5x squared plus 450x minus 50x plus 4,500. This 4,500 is not going to matter. You're left with this minus 5x squared plus 450, 400x. Take the derivative, set to 0. You get 10x is equal to 400. So x is equal to 40. Then you got to plug it back into this price because they want to now calculate the price. And it's going to be 90 minus 40. So the price that maximizes profit is $50. Yeah, we got it. It's right there. We got it. All right, let's just, I might quit soon. 20,000 spectators. 14,000 is the average, so you're going to work with 14, and you can't go above 20. Ticket price 75. Increase by each time we, so do 75 minus 5x times 14,000 plus 800x. You do the same thing. Multiply it out, find your parabola, take the derivative, set it to 0, find your x, but remember to plug your x back into your 75 minus 5x. That will be your actual price. And then x thousand is the price of this. So we have a weird price, and we have a cost. So I believe that this one, just to do it quickly, I'm not doing part C. Part C's are, you know, I'll have a look at them in the middle of the next lesson. So this one, we know that this is going to be your revenue. And it's x thousand of units, so we're at the end we've got to multiply by the 1,000, and that there's a cost associated with it, so revenue minus cost. And the important thing is you must put this cost all in brackets so that the minus distributes through to each thing. Maximize profit. So obviously, since they've given us a revenue, and notice that the cost is a parabola and the revenue is a straight line, we really are working with minuses here. So we're going to add just 5x. So that's really weird. But anyway, this 2,000, it all ends up being minus 14,999.98,000. That's what happens when 2,000 minus 15 million. Then it also ends up being minus 1,800,095. That's what happens when you subtract 5x. Oh. That's what happens when you subtract 5x from 1.8 million. And the last one doesn't matter. Squared. Taking the derivative of that, you're going to get minus 150x minus 179,995 is equal to 0. You're going to something weird's going on here. So that's a price. So if that's price per unit, I believe we have to multiply this thing by x, because this is a price per unit, and we don't know the units. So if I'm going to do it that way, I get 2000x minus 5x squared. That makes a bit more difference. So it still doesn't make sense, though. Because this minus applies to all these things. I'm going to get a minus 80x squared. This number's not going to matter, so let's just focus on the thing. And I'm going to get minus 1800 and the problem with it is this will be a minus number and this will become a positive, so I'll get a minus. Oh no, that makes sense. You can have a minus, but let's see which one's right. Saying it's 8150. No, that's the CDs. So we're talking about 1974 units. So they're saying how many units? Okay, let's do this one here and see if I got that one right. So just remember that this is the unit price times the number of units. And they're saying determine the level of sales that will maximize profit. It's weird. Anyway, minus 160 x squared is going to be equal to 1798,000. And I'm just going to see if I get that right. And that's going to be we have to lower that, so it's going to be a negative. Let me just clear my memory here and add it to the memory. And then the actual units is going to be that. Oh well. I don't really care about this one. It all depends what the revenue model is. This to me is profit. If that's the price, you got to multiply times the units. I'll try one last time. 1798,000 divided by 160, and that's going to be negative. So that's how many units I would then have to multiply. Open a bracket. 2000 minus 5 times that, close brackets. Yeah, so I'm way off. 19,000 units. So let's just try it with the number in there. Minus 5 times the number. Ugh, I did it again. I deleted the number. Jesus. Last time. There's the number. It's going in the memory. So I'm just going to take the base cost model. Yep, still don't get it. And my number of units doesn't match either. So a very confusing model. Just simply because that's a price. And the price is, I guess, going to be based on thousands of units. So if I figure out X, I figure out the unit. But then they say level of sales. and then they answer in units. Whatever. Don't care about that one.